Hi and welcome everyone. In this lesson and the next lessons, we are gonna discuss IT scheme or IT earthing system. So this will be divided into three videos. The first one, we are gonna talk about IT scheme and the effect of leakage capacitance. That's the first video. Second video about the method of detection of the fault. Third video would be about the maximum length of the circuit, same as what we did in the TN systems. So let's start by understanding what is exactly IT scheme and how it is gonna help us. So this type of earthing systems is used in places in which we would require high reliability. What I mean by this, like hospitals or airports. For example, in hospitals, I can't, there is a patient on a medical device or equipment. This equipment cannot be disconnected at any in presence of a fault. So if there is an issue with my own equipment, if there is an insulation breakdown, the equipment must continue operating. Okay, this is the most important features regarding IT systems. So what does IT? If you remember, IT, as we discussed before, I means isolated, my own supply, the neutral of the supply is isolated, either an open circuit like this, not connected to the ground, the neutral not connected to the ground, or connected to the ground via a high impedance. Like in this figure, you can see here the three-phase neutral. As you can see, the neutral of the transformer is connected to the ground or the earthing system via a high impedance, 1500 ohms. Now T refers to the new load side at which it's connected directly or solidly grounded to the earthing system. You can see that the protective earth here, we have the three-phase neutral. The protective earth is directly connected to the ground like this. Same as TT system. If you remember, the supply has its own earthing system. The load itself or the equipment, protective earth, has its own earthing system separate from the supply. It's the same case here for the load side. So the question is, how does this system will help me or protect me against electric shock? And how this system would have high reliability in places like hospitals? So here, as we said before, transformer neutral is not earthed or slightly earthed using a high impedance. If insulation broke down, nothing would happen as the circuit is open. Now let's explain this. So here we have phase A, or phase number 1. As you can see, this is an equipment that takes phase, which is 1, and here takes 2. So it takes a line-to-line voltage, or for example, a line, and it takes also the neutral, whatever the type of this equipment. Let's say A and the neutral, like this. Now this equipment has protective earth connected to its enclosure, as you can see here. So it has line, neutral, and protective earth. This one should be the neutral. Anyway, if an insulation breakdown in phase number 1, insulation breakdown, what will happen? It will touch the enclosure, which is connected to protective earth like this. So voltage will be on the enclosure, which is connected to the protective earth, like this. So how would the current flow? It will flow like this, from phase like this, all of the way through going to protective earth, to the earthing system, like this, back to the neutral of the supply, like this. This blue impedance or fault loop. However, if this transformer is isolated, meaning that it is an open circuit like this, I fault will be equal to 0, because here it will be an open circuit. What if it is not an open circuit? If there is a high impedance, I fault will be very small because it is equal to V over Z, the impedance of that whole loop. And since we have 1500 ohms here, this one will start going down. It will be very small value, as we will see right now. So let's go like this. I fault equal to V supply divided by Z or Z or the impedance. 230 volt for supply divided by Z, 1500 ohms. All of the others has an impedance, but it's very small, like 0.1 ohm. Very small for the phase conductor and the protective earth compared to this high impedance. So we can neglect the rest of the circuit. Now, if we divide this two, the I fault will be 153.33 milliampere. This is a current flowing like this. Okay, so what is the value of the fault? UF. So I fault, or specifically here, V touch voltage will be current flowing like this compared to the ground. So the voltage between this point and the ground, which will be I fault multiplied by the impedance of this path. Now, assuming that the R, the resistance of the earth, is 10 ohms, for example, okay, then V touch will be 10 ohms multiplied by I fault, which is 153.33 milliamperes, which is this mathematical equation. This will give us a touch voltage on the equipment, or voltage on the enclosure of the equipment, of 1.5 volt. Now we know that the dangerous touch voltage in dry conditions is more than 50 volt AC according to the IEC standard. So this is a very small voltage, so it is safe to touch the equipment even if we have an insulation breakdown. So since the transformer neutral is isolated, we have a very small fault current leading to very small touch voltage. Okay, so this is how we protect humans against this type of fault. Great. Does our circuit breaker will operate? No. Why? Because the fault current is very small, as you can see, and the circuit breaker will not detect this type of fault. So how can we protect if we would like to disconnect our circuit or protect our equipment, how can we do this? We can do this by using an RCD that compares the line current or the phase current and the neutral current. This one is the neutral, not phase 2, it is the neutral. So as you can see, the fault current, very small, 153.33 milliampere. Remember this value, as we will need it after some slides. Okay, so here we have no fire risk, no tripping required, and the machine can still run. Despite having this fault, it can still run with first fault. Now in IT system, we can have a second fault occurrence due to this type of fault. We will see this in lesson number 3. However, this fault must be detected, located, and cured before a second one happens. Now, how do we detect this? We are gonna see in the next video. Okay, again, the same case. We have this equipment here. You can see it takes the 3-phase and neutral, or it takes only 3-phase, a 3-phase load. You can see L1, L2, L3 because this is a delta motor. For example, we have L1, L2, L3 entering this one. If a fault happens between L1 and insulation breakdown and it touches the enclosure, the current will go like this through the protective earth connected to this enclosure here. like this, through the ground, back to the supply. Now we have an IT system, we have large impedance here. So if you would like to find the faulty current, it will be V supply divided by total impedance, which is 30 ohm for this earthing system, 10 ohm for this earthing system, and the high impedance 2000 ohm, leading to 0.112 ampere. If you would like the touch voltage, it will be between this enclosure and the ground, which will be I fault multiplied by 30 ohm, which is the impedance between it and the ground. 30 ohms multiplied by the current gives us 3.36 volts, same as the previous slide, very safe touch voltage. Okay, now as you can see here, value of current is 1533.3 milliampere. Okay, and I said if I wanna disconnect my RCD, I'm gonna or detect this fault and protect the circuit. I can add here an RCD that operates, for example, at 150 milliampere. So when we have this fault, this RCD will operate, and because the faulty current will be this value. However, there is one important part here. What is exactly that? When we have long distance between transformer and my own equipment, there can be the effect of capacitance, or the effect of leakage capacitance. We will see this right now. As you can see, for a network formed of 1 kilometer of conductors, let's say this conductor phases and neutral are 1 kilometer. Now there is a leakage impedance, leakage capacitance between each phase and the earth, neutral and the earth. Now why is this? Because our conductors have an insulation, and this insulation between it and the ground forms a capacitor. This capacitor at short distance is negligible. However, as the distance starts to increase, this capacitance starts to be more significant. So for example here, let's say that the leakage impedance to earth or capacitance is 1 microfarad per kilometer, and we assume that this distance is 1 kilometer. So each one of these will be, since we have 1 kilometer, the capacitance will be capacitance per kilometer multiplied by distance. So it will be 1 microfarad per kilometer multiplied by distance, which is 1 kilometer. This will go with this, leading to 1 microfarad per phase, including of course the neutral. So each one of these capacitance is 1 microfarad. Okay, so we want to know the value of leakage current during the fault occurrence. So first, XC is equal to 1 over omega C. Now the frequency to omega is 2 pi multiplied by frequency of the supply. In this particular case, I assume that my system works at 50 Hertz. So it will be 2 pi multiplied by 50 multiplied by capacitance, which is 1 microfarad, leading to XC of each of these components to be 3183 ohms. Now in normal operation, without any kind of fault, okay, in normal operation without any kind of fault, what is the value of leakage current? What is the value of leakage current? Leakage current will be simply V phase divided by XC. Now why is this? Because if you look at here, this one here, V supply equal to 230 volt. And this is a capacitance, has a reactance XC. So there is a small leakage current, I leakage, leaving in normal conditions. What is its value? Its value of I will be, or I leakage will be V supply divided by XC, which is 230 volt divided by this particular value, leading to 0.0722 amperes per phase, which is 1, 2, 3, about 72 milliamperes for each phase, for this one, and this one. What about the neutral? The neutral is already should have the same potential as Earth. It does not have any voltage here. So we don't have any leakage current here. We have only leakage current coming from these three phases in normal operation. Now, what is the problem exactly? The problem is that we have an RCD that detects leakage current or detects the leakage current, and the capacitance here would affect the original value. We will see what I mean right now. So when we have a fault between phase 1 and Earth, the voltage and current vectors are representing as shown, like this. So what does this even mean? Okay, so let's look at this figure and understand what I wanna achieve, okay? So let's say we have a fault between, again, phase 1 and the enclosure, like this. It means that the enclosure has V1, approximately V1. Now V1 is connected to the ground via a very small resistance, or it has the same potential as Earth. So Earth itself is now V1. Since the protective Earth is connected to the ground, and there is a breakdown happening here. So V1 here connected to the ground, so the ground itself became V1. A potential rise to the ground, like this. Okay, this is number one. Number two, now as you can see, since this one became V1, what would happen? For this particular one, we have here V1, we have here V2, we have here V3, we have here V neutral. So we have V1 and V1, no potential difference on this leakage capacitance. So here we have zero leakage current during fault condition. Now for the second capacitor here, we have a leakage current I2, which will be V1 minus V2, so V1 minus V2 divided by XC. V1 minus V2 is simply equal to V12 divided by XC. Similarly, for the third capacitor, V1 minus V3, the leakage current in this direction, like this. V1 minus V3, which means I3 is V13 divided by XC. For the neutral, V1 minus V neutral, which is 0, so it will be I neutral will be V1 over XC, or I neutral leakage current of this capacitor here. For this one here, it will be V1 minus 0 divided by this impedance. So I D, which is the I flowing through this large impedance, will be V1 divided by 1500 ohms. So in this particular case, or originally, we had only, during a fault, we had only ID, V1 divided by this impedance here, large impedance, V1 divided by this large impedance. If you remember, now we have three additional currents. We have one through the neutral, leakage capacitance of the neutral, leakage capacitance of phase 3, phase number 2. One does not have zero value. Now the problem here is that V1, 2 is a vector. Vector has a magnitude and an angle. We know that the line-to-line voltage is simply root 3 V phase with a certain angle. certain angle. It's changing based on what is the line to line voltage exactly. V12 has a different angle from V13, different angle from this one, V1, different angle from this one. And also we have XC itself, which is XC is also 1 over J omega C. So this one is negative J 3183. When it is down here negative J, it goes up like positive J. So what does this mean? It means that my own current here is leading by 90 degrees. Don't worry, I'm gonna show you this in this diagram, which I'm gonna explain, okay? So what I wanna say is that when I want I total, I have to add them in the form of vectors. I need I2 as a vector, plus I3 as a vector, plus In as a vector, plus ID as a vector, in order to find the total leakage current during this fault. Let's delete all of this. And let's see how I'm gonna get these vectors easily. So first I need to understand how can I draw this. Okay, so we know already that VA is equal to V max with an angle 0. VB is V max with an angle negative 120. VC equal to V max plus 120. So the three phases are shifted from each other by 120 degrees. Okay, great. So I can draw it like this. I can say VA, VB, VC, as long as I am preserving this 120 degrees. Now I can say that my supply has a phase shift of, for example, negative 180, like this. Negative 180, negative 180. It will be the same system, just inversed. So for example, VA minus 180 degree means it will be the opposite one, like this. VA. And VB becomes like this. And VC becomes like this, which is 1, 2, and 3. Now, in some technical guides, they do this in order to refer or point at the one which have a fault. So here we have VA or phase 1 has a fault, and we are pointing on or anchoring it like this, meaning that the ground became VA. As you can see, 1, 2, 3, A, B, C, and pointing at the ground. Okay, so this is exactly the same figure, like this. 1, like this, and the neutral. Now what I need is the first, I need V1 minus V2. V1 minus V2. Okay, so I have V1 here. V2 is in this direction. I need negative V2. Negative V2 means you are gonna reverse it like this. Negative V2. So you will have like this. 1 V1 negative V2. Now I want to add these two vectors. How can I do this? I can take this one here like this, parallel to it, negative V2, and then connect the beginning with the end like this. So it will be V12. If you look at this figure here, see this one here is exactly this one. V12, which is connection between 2 and 1 in the same direction as I just draw here. Similarly, if you want for this one, I need V1 minus V3. So we have them like this, 3, 2, 1. With these directions, I need V1 and negative V3. Add these two vectors together. Take this like this, parallel to it, negative V3. Take the beginning and the end, connect them like this. You will have V13, which is this one here. Same as what I have drawn here. So just vector summation. Great. Now, what about the currents? What about this one? V1 minus 0. So the voltage on it is just V1. Great. Now, what about the current I2 here? It will be, this is V12 divided by XC. Okay, now remember that the current here, we have a current here. What is the relation between current and voltage in a capacitor? So if we have a capacitor and the current I flowing through it, we have here potential V. What is the relation between I and V? What I mean by this, the relation in terms of angles. So if we have the current will be leading by 90 degrees. So if we have our voltage like this, the current will be leading by 90 degrees. Because this is a pure capacitance, like in this case. So any of these three currents, the current will be leading the voltage on each of these capacitors. So let's take it step by step. So we have here, the first one here is VC2. This one, VC2. So the current will be leading by 90 degrees like this. IC2, leading by 90 degrees. So if you look at here, like this, IC2, which is this one, we took it right here, like this. Similarly, for C3, which is V1, 3, this one, this vector here, like this, the current will be leading by 90 degrees, so it will be greater than it, or leading by 90 degrees, which you can see like this, IC3, which is this one here. This one parallel to the one that I just draw here. Now, similarly for the neutral, we see that the neutral here is this one. This is V1. So it will lead by 90 degrees like this. I1 or IN like this. So this vector here. Okay, so we have drawn these three currents. Lastly, this one will be in phase with the voltage because this one assumes a pure resistive. So the current flowing here is in phase with the voltage, which is V1 minus 0. So they are having the same, the ID1 is the current flowing here in phase with the supply. So we have drawn the vectors. Now I can add them in the form of vectors like this. Okay, so let's go all of this. Fault current will be equal to 0.0722 and the angle 0. So look at this is the value as a magnitude for each one. V phase 230 divided by 3183, which is 0.0722 amperes. So one has an angle 0. Which one exactly? ICN. So ICN is V1, which is the phase value, divided by XC. However, it has 0 angle according to this diagram which I have drawn. ICN 0 angle. This is the 0 angle here. Now for the second one, which is the current, here is 30 degrees, so IC2, which is this one, will be V12 divided by XC. So it is the line to line voltage. Now phase voltage, so we will take this value here multiplied by root 3. Why? Because we have V line to line, meaning this one will multiply by root 3. So 0.0722 multiplied by root 3. Similarly, for VC2, for IC3, it is also line to line because V1 minus V3. So we multiply it by root 3 again. Now for the angles, when we measure this angle here, it will be 30 degrees. When we measure this angle, it will be minus 30 degrees. You can get it from this phasor here. 30 degrees and the negative 30 degrees. Now lastly, for this one, according to this diagram, it has a negative 90 degrees. Negative 90 degrees. Its magnitude is simply V1 divided by 1500, which is 0.1533, which I obtained in the first slide of this video. When we add all of these vectors together, I'm gonna get a magnitude and a phase. I don't care about this phase angle. It will be 3 to 7 milliamperes. This is the magnitude of the current. Now look carefully here. We started with 153.33 milliamperes, and now the current became 3 to 7 milliamperes due to these leakage capacitance. Okay, now if you don't understand this one, you can do it normally like this. VA, VB, and VC, and do the same procedure. This one V1, V2, V3, get the line-to-line voltage and get the currents. You will get different phase from this one, different phases from this. However, in the end, you will get the same magnitude but different phase. Neglect the phase, only what I care about is the magnitude. So this is the effect of leakage current. Now, when the connection at the first fault is achieved by an RCD, now the rated residual operating current of the RCD shall be selected to be less or equal to the current which circulates on the first fault to earth. So what I mean by this, you have seen that instead of 153.3 milliamperes during fault, it is actually more than 300 milliamperes. This value here. So during fault, I have this value. So when I adjust my RCD, it should be operated at least 300 milliamperes, not 150 milliamperes as before. Why? Because 150 milliamperes neglect the effect of these capacitance. Now, what if I don't know? What if I don't have the knowledge of the system and cannot estimate these capacitance? What should I do? Well, there is a rule inside the IEC standard that tells you if the current, where the current circulating during the first fault is not known or cannot be calculated, I can't estimate the value. What should I do? The current in milliamperes can be for IT installations be estimated to be 0.5 the value of the rated power of the transformer in kilovolt ampere. What does this mean? If I have a transformer of 1 megavolt ampere, meaning 1000 volt kilovolt ampere, the IEC tells you, hey, you can estimate that current to be 0.5 multiplied by that value, 1000. It will give you about half of it, 500 milliamperes. So 0.5 multiplied by your rated power gives you current in milliamperes. So if I have transformer 1 megavolt, the leakage current 500 milliampere. So this is the current during the first fault. So I have to, if I put RCD, I have to make its value from 500 and above, or at least 500 milliamperes. Now, if the automatic disconnection of supply at second fault is achieved by RCD, this is what we are gonna discuss in lesson 3. But just remember this note, that if you are gonna use RCD and you don't wanna make it operate at the first fault, it must be double the value that I selected before. For example, when I said that the 500 milliamperes, this is for first fault. If I don't want this equipment to be disconnected, I will select it to be double the value. Why double the value? This will operate during second fault that we will discuss after the next lesson. Don't worry if you don't understand what's the second fault, I'm gonna discuss in detail. But just I wanted to mention this to be remembered in the next in the lesson after the next one. So I hope you now understand the effect of leakage capacitance in IT scheme and how do they affect the operation of RCDs, and I have to take them into consideration. In the next one, I'm gonna talk about the detection method, very easy and quick video, and then we are gonna go to the second fault, which will be a long video. Thank you for watching this lesson in our course for electrical design. If you would like to learn how to design electrical systems from scratch, we have a large course on electrical design in which you are gonna design electrical systems in AutoCAD, Dialux, Excel, ETA. You will also learn how to select circuit breakers, cables according to NEC and IEC standards. We are gonna go step by step in AutoCAD and how to draw the lighting circuits. We will also learn how to do the lightning protection systems in addition to SPD or surge protective device. This is a large course, as you can see here, which is gonna help you in becoming a professional electrical design engineer. Thank you and see you in our course for electrical design.